Assalamu alaikum warahmatullahi wabarakatuh. So we were discussing number system, and in the previous lecture we discussed three types of number systems: binary, denary and hexadecimal, or binary, decimal and hexadecimal, and we saw how to convert between these two. Now today we are going to start with a new topic that is again a part of section number 1.1. This has been a new addition in the new syllabus, whereas it wasn't there in the old syllabus. That is binary addition, binary multiplication and binary division. Now if you need to perform binary addition, firstly both numbers should have equal number of digits. If one has lesser digits, add zeros to its left until both numbers, not digits, have equal digits. For example, you cannot add because they have unequal number of digits. This has 4, this has 3, so you'll have to make it into 4. How? By adding a 0 on the left side. Now you can add. Okay. Rules for addition: 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 10, or 0 is the answer and 1 is carried forward. 0 0 0 is 0, 1 1 1 is 11, or 1 is answer and 1 is carry. 1 0 1 plus 0 plus 1, or 1 plus 1 plus 0 equals to 10, or 0 answer and 1 carry. You have to remember these rules. Okay. Now add the 8-bit binary values, this number and this number. So first of all, write it in form of columns. This is the first number, this is the second. They both have 8 bits, so we do not need to add a 0 on the left hand side. Now 1 plus 1 is 10, so 0 is placed here and 1 is carried. Now 1 plus 1 is again 10, so 0 is here and 1 is carried. Now 1 plus 0 is 1, 1 0 is 1, 1 0 is 1, 0 0 is 0, 0 1 is 1, 0 0 is 0. So this is the answer of our addition. Simple, right? Now another thing which we have in binary addition is an overflow error. The largest binary number that an 8-bit register in a CPU could possibly hold would be 11111111, equivalent to the denary number 255. If one more bit was added to this number, it would push the number above the capacity of the register and would cause an overflow error. For example, try adding 100 10 100 and 100 11110. This is the first number and this is the second number. 0 0 0 0 1 1 1 1 10, 1 is carried, 1 1 10, 1 is carried, 1 1 1 11, 1 is here, 1 is carried, 1 0 0 1 0 0 0, 1 plus 1 is 10, 0 is here and 1 would be carried over here. Since there is no number, so this one would become the 9th bit. But if you have an 8-bit register, it cannot contain 9 values, so this is known as, this 9th bit or answer is known as overflow error. When the addition of two binary numbers give an answer which is having an extra bit, we say that we have encountered an overflow error. For a CPU to divide next we have logical binary shifts, mean divisions and multiplication. For a CPU to divide a binary number, the number needs to be shifted to the right, whereas if the CPU needs to multiply a number, it is shifted to the left. Each shift is equivalent to multiplying the binary number by 2, and each shift right is equivalent to dividing the binary number by 2. For example, divide 1010111 by 4. Now this is the number and its denary is 171. Since each shift means division of 2, so for dividing 4 we need to perform 2 shifts, because 2 into 2 is 4. So shift 1, all the bits take one jump towards the right hand side. Okay, so this one becomes obsolete because it jumps out of the boundary, and this one comes over here, this 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 comes into its place, and in its place we have a 0. Since there is nothing, so we add a 0. Now we perform the second shift. This comes over here, this one comes over here. Let me draw some arrows. So this one goes over there and is deleted. Then we have this 0 comes over here, this one comes over here, this 0 comes over here, this one comes over here, this 0 comes over here, this one comes over here, this 0 comes over here, and over here we introduce a new 0. And this is the second shift, so this would be our answer, and the denary value for this is 42. Actual arithmetic answer for 171 divided by 4 is 42.75, but we only get in logical binary shift we only get 42. This is because working with binary doesn't use decimals. You can only represent whole numbers, so only positive binary integers, so any decimal part is always discarded. These bits are called least significant bits, and when they are shifted beyond the right hand column, binary data loses precision due to overflow. Because there is no 9th bit over here, so this part is lost, hence we cannot represent the decimal part. Now let's have an example of multiplying by 2. This is the number and we have to multiply it with 2. Its denary value is 92, and one shift means multiplication of 2, so we would perform one shift. And how do we do that? This 0 comes over here, this 0 comes over here. Basically, okay, let's start from here. This 0 jumps over there and becomes overflow. This one comes over here, this 0 comes over here, this one is jumped over here. Okay, hold on a minute. Now this is more appropriate. This 0 comes over here, this one comes over. We have to perform left shifts. So this 0 comes over here, this 0 comes over here, this one comes over here. Let me draw arrows. This 0 comes over here, and this 0 comes over here, and this one becomes this, this one becomes this one is shifted over here, this 0 is shifted over here, this one is shifted over here, and this 0 is shifted beyond the value 8-bit register value, so this is discarded, whereas the place which is left now we fill it with a 0 and we get the denary answer as 184. This is clearly a limit to the number of shifts which can be carried out if the binary number is stored in a 8-bit register. Eventually after a number of shifts the register would only contain zeros. For example, if we shift 0 1 1 1 0 0 0 0, denary value 112, 5 places left, the equivalent to multiplying by 2 raised to power 5 means 32. In an 8-bit register we would end up with 0 0 0. Why? Because each number is going to take 5 jumps. So this 0 would jump 5 times, this one would jump 5 times. Let me show you. 0 1 1 1 0 0 0 0. This is the number. Now if you make it jump 5 times, so what would happen is that basically each number is going to move 5 times. So this 0 is going to take a shift 5 times towards the left. It would be eradicated. This one is going to take a shift 5 times, eradicated. Again this is deleted, this is deleted. This 1 2 3 4 5 6. Now if this 0 takes a jump of 5, then that means 1 2 3 4 5. This 0 would come over here, and this 0 would come over here, and this 0 would come over here. How, you may ask? Because we have multiplied it with 5 shifts. This 0 comes over here, and again this 0 comes over here, and the places which we are left, obviously we are supposed to fill them with 0 0 0 0. So all of it becomes 0. Whereas if you multiply 112 by 32, you should not be getting the answer as 0. See, if I open the calculator and I multiply 112 with 32, I should be getting this answer, 3584. This is never equal to 0, so this would result in the generation of an error message. So just remember, there is always a limit to how much multiplication and division you can perform on a register. The next thing which we have in section 1.1 is 2's complement. Now what is 2's complement? Binary numbers only have two values, either a 0 or a 1, so putting a negative sign before number isn't possible. One of the methods used by modern CPUs to represent negative numbers is called 2's complement. To represent a negative number, CPUs are first set up to see the furthest or the further left bit as a sign bit. So if sign bit is 0, number is considered positive. If it is 1, number is taken as negative. Let's have a look at an example. Let's suppose this is an 8-bit register, so the leftmost bit is declared as a sign bit. Okay, this one. So how do you write it? Invert all the bits, change all zeros to ones and ones to zeros, and add 1. This is the simple way of write down 29 as 2's complement format. How do you do that? Since 29 is a positive number, so in the leftmost bit you write a 0, and then you simply write the value for 29 in binary. That would be this number. Okay, and we can and for confirmation we are going to check 16 plus 8 plus 4 equals to 29. Whereas if you have to write minus 58 as 2's complement, since it is a negative number, the minus 1 to 8 or the most left bit, left column would have a value of 1. Step 1, convert 58 to binary, and it is going to give us this value. We are going to check it for precision, and yes, it gives us 58. Step 2, invert the binary, means in place of 0 write down a 1, and in place of 1 write down a 0, and then add 1 to it. 1 plus 1 is 10. 1 plus 0 1, 1 0 0 0 0 1 1, so we have added 1 to it. Okay, and the next step, fill the grid, given grid. Here we go, cross check it for precision. Minus 1 to 8 because it has a value of 1, plus 64 plus 4 plus 2 equals to minus 58, and we have our answer. When applying 2's complement, it isn't always necessary for a binary number to have 8 bits. The examiner may give you 6 bit, 8 bit, 12 bit, or any other number of bits register in the paper. Just remember that whatever would be the leftmost bit, it would always have a negative sign. In the Cambridge exam, you will be given a grid like this, and if the leftmost bit is negative, it has a value of negative, the examiner is going to give you these values as well, whatever it is, minus 64, minus 32, minus 128, minus 256. So just remember that you have to convert the given number, you have to represent the given number in 2's complement format and not in plain binary. Okay, so I hope you have understood. If you have any problem, feel free to ask me. Take care. Allah Hafiz.